Right, hello everyone. So this is a derivation for terms for adiabatic expansion. Okay, so adiabatic expansion means that we've got no heat exchange with the external environment. So in this situation, we can quite easily say that delta Q equals 0, so no heat exchange. What this also means is that our change in internal energy therefore becomes a simple consideration of the pressure being constant with a change in volume. So because it's adiabatic expansion, we're not exchanging heat with the external environment. The internal energy changes as a result of us allowing the volume of our cylinder to change. So work is effectively being done at the expense of external energy, so the temperature is going to decrease. Okay. So what we also know already is that this change in internal energy is related to the specific heat at constant volume and the change in temperature that's going to happen. As the cylinder expands, the volume gets bigger, the temperature goes down. So from these two equations, what we can then say is that the specific heat capacity at a constant volume with a change in temperature is related to the pressure being constant and the volume change that we're going to experience. So if we're considering a quasi-static situation, then we can think about our ideal gas equation. So we can think that PV equals RT. In this situation, if we're just going to consider a single mole, we've just lost the N term because it's 1 mole, so N equals 1. And for small changes that we're expecting to happen, we can just consider a small change in the volume, small change in the pressure, small change in the temperature. So if we think about the ideal gas equation and put these small changes in, we can say that pressure being constant with a small change in volume plus the volume being constant with a small change in pressure is going to be equivalent to our ideal gas constant and a small change in temperature. Okay, so if we rearrange this equation, we can get a term for dt, which is P dV plus V dP over R. Okay, so we've got a dt term here that we can now substitute into this term here. So when we do this, we get CV over R, PD plus V dP equals minus P dV. Okay, now we're just going to do a little bit of rearranging of this equation. Okay, now what we'd like to do here ideally is lose this R term. So we want to get this in terms of the specific heat terms. So what we saw in an earlier lecture was that the ideal gas constant is actually related to the difference in these two specific heat terms. So it's the difference between the specific heats at constant pressure and the specific heats at constant volume. So we can then just substitute this into here, and again we'll do a bit of quick rearranging. Okay, now on both sides of the equation here we've got a CV/PdV term, so we can just lose that one there, and we can bring this term across to the other side. So this gives us CV VdP plus CP PdV equal to 0. Okay, so let's just rearrange this a little bit more. So VdP plus Cp over Cv, pressure, change in volume equals 0. Okay, now at this point what we're going to do is define a term that we're going to call the ratio of specific heat. So this has the symbol gamma, and this is just the ratio between the specific heat capacity at constant pressure and the specific heat capacity at constant volume. So by doing this we can substitute a sort of term in that relates to the gas that we're working with, and it simplifies the equation a little bit. So we then get this term V dP plus gamma P dV equals 0. Okay, so we'll just rearrange a little bit more to get terms in terms of pressure and one in terms of volume. So we have dP over P plus gamma dV over V equals 0, and we want to get rid of the differential terms by integrating. So integral of dP over P plus gamma integral of dV over V equals 0. So we get ln of the pressure plus gamma ln of the volume plus some constant equals to 0. Okay, so by our laws of logs, it's pretty straightforward to see that PV to the power of gamma equals a constant term. Okay, now the thing to note here is because of the way that the specific heat terms work, that gamma, draw that bit better, is always greater than 1. So this means that on an adiabatic curve, it's always going to be steeper than an isothermal curve on a PV diagram because this is greater than 1. We can use this term for our adiabatic expansions, but we can also say that because we know PV equals RT, we can also say that in that situation, TV to the gamma minus 1 must also be a constant, and we can also say that pressure to the 1 minus gamma times by T to the gamma is also a constant. So we've got a few different terms there that relate the pressure and the volume to this gamma term, which is just determined by our specific heat values. We've got similar expressions here for the temperature and the volume, and the pressure and the temperature.